How do we measure things in astronomy? What units do we use? And how do we actually measure things that are way out in the cosmos? Well, we're going to talk about this all semester long, but let's first off start talking about distances. Around your normal life, we're very familiar with miles and or kilometers. And these are things that I think you have kind of a gut instinct for because of the fact that you drive so many miles to your friend's house. You drive so many miles to Burger King, wherever your favorite food joint is. You kind of know where things are. You may not be so familiar with kilometers unless you've lived in Canada or in a foreign country, but well, you've got a gut instinct for distances. The challenge with astronomy is everything is so far away that if I measure it in miles, it's hard to wrap my head around. And so astronomers have come up with different units. And one of the units they've come up with is something which is called the astronomical unit. Now, I'm putting a star by this because you should know the astronomical unit. It's fair game on quizzes, tests, labs, etc. Astronomical unit is abbreviated 1AU, and it is the average distance of the Earth to the Sun. Now, one astronomical unit is 93 million miles. It's a really, really, really big distance. If I say 93 million miles, my head kind of hurts and says, oh, it's big. But aside from that, I don't have a feel for it. But because we want to compare how far the Earth is from the Sun compared to, let's say, Jupiter or Pluto or a distant star, the AU is useful. Now, why does this say average distance from the Earth to the Sun? Well, as the Earth rotates around the Sun, our orbit is not perfectly elliptical. Not perfectly circular. There are times that this distance is a little bit smaller, and there are times when this distance is a little bit larger. Now, not a lot smaller or larger. The Earth's orbit is actually close to being a circle around the Sun, but not exactly. And this slight change in distance is why we have to say average, because of the fact that the Earth does get a little closer and further in her orbit. Another unit that we're going to use in astronomy is the unit, the light year. Now, this actually is a distance unit, but it can be very, very confusing because look there, it has the word year right in it, and year is definitely a time unit. So how do you tell the difference, or how do you know? You just have to know that a light year is a distance unit. So what does this mean? Well, if you went out tonight and you stood on planet Earth and you shone your flashlight out into space, 1 year later, the light from your flashlight will have traveled 1 light year. It's the distance light will travel in 1 year. Now, light is the fastest thing that we know of. We don't know of anything faster than the speed of light. And so 1 light year is a long, long, long way. So let's put this into perspective. The moon is about 1.3 light seconds away. If you shine your flashlight up on the moon, it takes about a second, a little over a second for that light to get there. The sun is about 8.3 light minutes away. So beams of light from our sun that come down and strike the Earth take about 8 minutes to get to us. Alpha Centauri and its neighboring sister star, Proxima Centauri, are 4.4 light years away. These are the closest stars to us, and the light from them, when we see them, is over 4 years old. The star could be gone, blown up, whatever, and we won't know it till 4 years afterwards. There are globular clusters that are 25,000 light years away. We'll talk about globular clusters. They're beautiful structures of clusters of galaxies. And our closest galaxy to our Milky Way galaxy, the Andromeda galaxy, is 2.5 million light years away. That's a nutty big distance, but that's why we use light years. If I measured this in miles, oh, we'd have numbers with lots and lots and lots of zeros behind them, and we could, but it would be really hard to wrap our heads around. When we start talking about outer space, we also have to talk about scale sizes of things. Sometimes that's a nice way to model in our heads how big something is. So to put this in an idea across, if the Earth is one Earth size, the sun is 1 times 10 to the 5th times bigger. Now that means 100,000 Earths could fit into our sun. The challenge is, even in this picture right here, that's not even close. You almost never see accurate scale pictures because of the fact that for this little sun to make an Earth, I cannot draw a dot small enough to accurately represent how small the Earth is compared to that little picture of the sun. The sun to the outer edge of the solar system is 1 times 10 to the 7th, so that is 10 million times further from the sun out to the distant edge of the solar system. The distance to the next galaxy is 1 times 10 to the 15th, much bigger, and the farthest known reaches of our of the cosmos is 1 times 10 to the 20th. So it's massive nutty big, how big things actually are in space. All right, that will do for the moment. I'm going to ask you to watch a couple videos on time scale, size scale, to hopefully help put this in perspective.